All right, as promised, here's the lecture about stressing out those chemical reactions and unbalancing that equilibrium. It's called Le Chatelier's principle. Let's get started. So the last lecture had to do with chemical reaction rates and equilibrium, and we saw, if a chemical reaction is reversible, that at some point the forward reaction is going to equal the reverse reaction, and we're going to get what's called dynamic equilibrium. And it's basically kind of cruise control for a chemical reaction. In this lecture, we're going to talk about disturbing the chemical reaction's equilibrium. So here's our question. What happens when a chemical system at equilibrium is disturbed? Well, a French chemist by the name of Le Chatelier, I'm sure you could say it differently in French, but I don't speak French. So Le Chatelier is the best I can do. He came up with this principle that said when a chemical system is at equilibrium and it's disturbed, the system shifts in a direction that minimizes the disturbance. So it'll speed up in one direction or the other in order to kind of bring it back to equilibrium again. So consider the following reaction at equilibrium. We have N2O4 breaking down to NO2. Okay, and that kind of goes back and forth. We can have the degradation of dinitrogen tetroxide to nitrogen dioxide, or we can also have nitrogen dioxide come together to form dinitrogen tetroxide. Okay, so this is a chemical reaction that goes in the forward and reverse directions. All right, so if this is nice and peaceful at equilibrium, and then we disturb it, okay, by adding more NO2 on this side. So if we add more NO2 on this side, what happens? How do we kind of bring that back down to, our equilibrium level again? Well, we're going to speed up the direction that way, the reverse direction. We're going to shift it, we call, to the left. We are going to speed up the direction of the chemical reaction towards the left in order to lower the concentration again to the equilibrium state. Okay, so we're going to decrease that increased concentration of NO2 and bring it back down, all right, by shifting it to the left. So we're going to speed that up. Now, if we add, on the other hand, more N2O4, okay, so we add a bunch of that, how do we get rid of all that excess that we just added? Well, we shift it to the right. Okay, so shifting it to the right will speed up the breakdown of N2O4 into NO2, and so it'll bring down the concentrations of N2O4, and okay, we'll get equilibrium kind of back again. All right, so that's basically the concept of Le Chatelier's principle. So in summary of what I was just drawing on the last slide, if a chemical system is at equilibrium, increasing the concentration of one or more of the reactants causes the reaction to shift to the right, to make more products, to get rid of those reactants. Increasing the concentration of one or more products causes the reaction to shift to the left, towards reactants, to decrease those products that we just increased. All right, so we want to find that happy balance again. So let's take a look at this example. What is the effect of adding more CO2 to the reaction? All right, so here's our reaction here. We've got calcium carbonate breaking down to calcium oxide and carbon dioxide. So if we add more CO2 on this side, well, what will it do? How do we bring those levels back down? We are going to shift it to the left. Okay, so if we add more CO2 to the reaction, we're going to shift left. Okay, to bring that back down again. We're going to speed it up to make more calcium carbonate on this side so that we bring down the levels of our CO2 again. Now, what if, though, we add more CaCO3 or calcium carbonate to the reaction? Well, if we've got a much more concentration on this side, okay, we're going to shift it to the right. So we're going to say shift right. Okay, and we're going to bring back down those levels towards equilibrium again. Okay, so that's how it works with concentration of reactants and products. Let's take a look at another example. Here's a you try it example for you to do at home. So consider the following reaction in chemical equilibrium. So here we have BrNO decomposing to NO and Br2. What is the effect of adding more Br2 to the reaction? All right, so I'll do this one together with you, and then you can do the other two on your own. So if we add more Br2, okay, on this side, way to bring it back down, bam, shift it to the left. Okay, so shift left. Now, the next one for you to do is, what if we add more Br and O on this side, right? But let me focus you on the last one. What about removing Br2? Okay, so actually let's do that one together, just because we haven't seen that before. All right, so if we remove Br2, okay, from this reaction, which way will it be shifting in order to make Br2? All right, well, in order to make Br2, we got to, we have to break down the BrNO, right? So it's going to shift to the right in order to make the Br2, the bromine gas, that we are losing or removing in this instance. Okay, so that's how that works. All right, so you do the second one, and then let's move on. All right, so we talked about concentration. Now let's take a look at volume. Okay, changing the volume of a gas and how that relates to Le Chatelier's principle. So remember, when you decrease volume, you increase pressure. Remember, that was Boyle's law, right? So if you decrease the volume of something, you're going to increase its pressure. So, it's like this down here. If you decrease the volume, if you push down on the piston, okay, decrease the volume, you increase the pressure that's inside of that little container. Okay, you got more collisions going on, so you get more pressure. If you increase the volume, you decrease pressure. So imagine if, we started out with the one on the right and we're going over to the left. So we increase the volume. Well, now we got more space, so we're going to decrease pressure. All right, so that's a little review of Boyle's law. Well, if the volume of a gas reaction mixture is at equilibrium and it changes, the pressure changes and the system shifts to minimize the change. Dun, dun, dun. Okay, so we can make more products or more reactants in a gaseous reaction just by increasing or decreasing the pressure. Let's see how that works. So consider the following reaction. Nitrogen gas and hydrogen gas react to form ammonia, NH3. All right, so this is a reversible reaction, meaning that NH3 can decompose back down into nitrogen gas and hydrogen gas very easily. So if we take a look, if this is at equilibrium as we speak, we say, what happens if we raise the pressure? Okay, so what happens if we increase the pressure? So it basically looks like this picture down here. We've got nitrogen gas and hydrogen gas, okay, and then we increase the pressure, right, by decreasing the volume. And so what happens? Well, with gases, it's a little strange. We have to take a look at the moles of reactants versus the moles of products. In the beginning, our reactants, we have 3 moles of H2 and 1 mole of N2. So that in total is 4 moles, right? And on this side, our product side, we have 2 moles. So if we increase the pressure, we're going to want to shift it to the side with the least number of moles so we can take up less space. So that's exactly what happens. You can see it in our picture. As we increase the pressure, we're going to be making more NH3, okay, because it's less moles that take up less space. Therefore, the pressure inside is lowered. Now, if the opposite happens, if we increase the volume, Okay, that means, we're basically going this way where we increase the volume. All right, now we got a ton of space, so we can make, as much molecules as we want. All right, so it responds by shifting to the side that will bring the pressure back up. So we're going to shift it this way to the left now in order to convert the 2 moles of NH3 gas to 4 moles of the total of nitrogen and hydrogen gas. Okay, so we shift it to the one with the most moles if we decrease the pressure. All right, so here's a little summary. If system is at equilibrium, decreasing the volume causes the reaction to shift in the direction that has fewer moles. All right, so if we decrease volume, you shift to fewer moles of the gas. If you increase the volume, all right, you shift. That means, remember, increasing volume means decreasing pressure. So if you decrease pressure, you shift towards the more moles. All right, decreasing volume means increasing pressure. Okay, so just keep those in mind. Now here, if a reaction has equal number of moles, then there's no effect. Changing the pressure will not affect it at all. It won't shift. It'll just stay equilibrium. Okay, there's no way for it to decrease or increase the pressure in that way. All right, so let's take a look at this example. What is the effect of decreasing the volume of the reaction? And the second question is, what if we increase the volume? So first thing let's do is figure out how many moles of reactants and products we've got. So here we've got 2 moles of reactants, and the product side we have 2 plus 3, that's 5 moles of products. All right, so what is the effect of decreasing the volume? Well, if we decrease volume, right, that means we are increasing the pressure. So we need to shift it to this side with fewer moles. So we need to shift it in this example to the left. We need to shift it towards the side that only makes 2 moles of gas rather than 5 moles of gas. So in this way, we're going to shift it left. If we increase the volume, if we let off the pressure, so decrease the pressures, increasing the volume, then we can shift it to the side where the more moles. So in this case, we're going to that's going to shift it to the right. Okay, because we've got more moles of product on the right. Let's take a look at an example that you can try on your own. Consider the reaction at chemical equilibrium. So this reaction is at chemical equilibrium. It's a reversible reaction that has to do with gases. All right, so SO2 plus oxygen is going to equal SO3. What is the effect of decreasing the volume? What is the effect of increasing the volume? You figured out. All right, so we've talked about concentration, we've talked about pressure, and now we're going to talk about temperature. If the temperature of a system at equilibrium is changed, the system shifts to counter that change. All right, so we can see here in this picture, all right, that so this is a reaction at equilibrium where we have reactants and products, and it emits heat. So this is an remember this is exothermic reaction. If we increase the temperature, okay, so that means we increase the heat. Look which way it shifts. Shifts to the left, okay, to get rid of some of that heat, to absorb some of that heat back in, right, and to lower it overall. Now, if we take a look and we decrease temperature, right, so if we take away this heat, then it shifts to the right to make more heat, all right, so in order to get it back to equilibrium again. So that's the way it's going to work. So let's take a look at some specific examples. All right, quick little review here. Exothermic reactions emit heat, right? So heat will be on the product side of an exothermic reaction. So if we raise the temperature, all right, that means we increase heat. We're going to be shifting it to the left. If we lower the temperature, if we get rid of the heat, we're going to shift it to the right to make more temperature. Now, an endothermic reaction, Remember, absorbs heat. So heat is going to be a reactant in an endothermic reaction. So if we increase the heat on this side, we're going to shift it towards the right so we can get rid of that heat. We can use it up to make more products. However, if we decrease the heat, if we take it away, we're going to shift it to the left in order to make more heat again and more reactants. So here's an example. This is one that actually we saw at the beginning of this this chapter. All right, so if we have N2O4, okay, it's a gas. It's actually a gas that is prevalent in the atmosphere. Okay, and so we have this gas. It's colorless. Okay, and we add heat. We get it to break down into nitrogen dioxide, which is a brown color. Okay, and so if we add a lot of heat to this colorless gas, it breaks down to a brown color. Now, check this out. This has to do with smog and why. It's not the smog like really goes away during the colder months. It's just that this chemical reaction is occurring. So in the summer, okay, it's hot, right? So we increase the heat. Okay. And so if we increase the heat in our atmosphere, we're going to get this N2O4 gas in our atmosphere being broken down into nitrogen dioxide, which makes brown, nasty smog that we can totally see. Okay, like everywhere. It's gross. All right. Now, on the other hand, during the winter months, okay, during the winter months, it's cooler. That means we're decreasing the heat. All right, what happens if we decrease the heat? Well, this reaction is going to shift left. It's going to shift to make more colorless gas in our atmosphere. And so the smog, quote unquote, goes away. All right, or basically it just shifts back to N2O4, which is a colorless gas. Okay, so this doesn't account for all of the smog, okay, that we see, but it kind of does account for some of the differences we see in smog levels in the summer versus the winter months. All right, so this is just a little picture of Paris, because we don't live there, and the Eiffel Tower. And so in this picture on the right, we can say which months out of the year is probably this picture. Right, exactly. It's in the winter months, or the colder months. All right, because we've got less brown gas being, in the atmosphere, versus this guy. This guy's probably taken in the summer months or the hotter months in Paris, where that colorless gas gets shifted towards the brown nastiness that we see. All right, here are some. This is the last slide of this lecture. Here's some you try it, where I'll do the first one with you, and then you can do the second one on your own. Okay, so the following is an endothermic reaction. All right, so we need to know that because in these two equations, heat is not actually written in, right, as a product or reactant. So endothermic means that heat is on this side. Is our reactant side. It absorbs heat, so we need heat for the chemical reaction to take place. So, if it's endothermic, what is the effect of increasing the temperature of the reaction mix? So here we make it hotter. If we increase it and it's on the reactant side, that means, bam, it's got a shift left. I'm sorry, that's right. Haha, silly teacher. Shifts right. Now, if we decrease temperature, take it away, take the heat away, it's going to shift to the left to make more heat, to get back to equilibrium. All right, so that's how that works. Now, in the second one that you guys are going to do, this one is an exothermic reaction, so that means heat is on this side as a product. All right, so you take a few minutes to figure out what's going to happen. Which way is it going to shift? if you increase the temperature versus decrease the temperature. All right, and as always, if you have any questions, come ask me at the next lecture. We'll see you then.